Hey students, welcome back to Calculus with Mr. Beck. Today we're going to be talking about sections 2.1 and 2.2 in our book. 2.1 is all about the derivative. What you'll find is in chapter 1, we did a lot of the skills which led up to the idea of the derivative. Today we're going to actually do it. 2.2 is going to be about derivative rules, at least the beginning of our derivative rules. And the first derivative rule is the power rule that we're going to talk about. So let's get into it. I want to start by taking a look at this equation y equals 4x minus 7. Y equals 4x minus 7, if I want to know what is the slope of this function everywhere, obvious answer is, hey, this is a line, so the slope is going to be 4 everywhere. But then if we take a look at an equation such as y equals 2x squared minus 7, I can say, all right, we know that the slope is going to be 4 somewhere, but what's the slope everywhere else? So our big goal is, can we determine the slope of a function at any given point? To do that, we're going to begin by talking about the slope of a secant line. So what I've done is I've built 2 points here. The first point is x f of x. Second point is x plus delta x, f of x plus delta x. And the reason why it's written this way is because we want to establish everything going from a single variable x. We want to try to get everything in terms of x as much as possible. We call this calculus of a single variable because then if that single variable changes, how does everything else change and correspond to that? So the second point we're going to say is going to be a small distance delta x away. So we get our new point x plus delta x, and then thus we get the coordinate that I have right there. So the slope of the secant line is what we call the average rate of change because it's the amount of change between points. I kind of relate this to speed. If I have a certain distance I need to go, let's say we've gone 6 miles, and in 6 miles, it's taken let's go ahead and do 6 minutes just to make life easier. 6 miles in 6 minutes, what that means is we're going to be traveling 60 miles per hour. So we can measure that change by change in distance over time. But that would be the average speed. Does that mean that I've gone 60 miles per hour the entire time? Not necessarily. I could be going faster. I could be going slower. That's just my average change. So that average change, if I use the 2 points that I have listed here, those 2 points once again are x f of x and x plus delta x, f of x plus delta x. You'll see that that corresponds to slope y2 minus y1. Now I didn't write it on here, but x2 is x plus delta x minus x, and what ends up happening are those x's are going to cancel. We just are left with delta x. Now we're taking that secant line, we're saying what's the slope between 2 points, and then we're going to turn that into what is the slope at a single point. The slope at the single point is what happens when, I'm changing colors here, what happens when that delta x gets smaller and smaller and smaller. So that second point that I have here, what happens if that second point were right here? So there's my delta x. Now let me erase that and say, okay, what happens if that second point over here? And there's my delta x. And we get closer and closer together until we get to that second point right there, which forms a tangent. Now, this will never actually be the same. Delta x has to be some number. But what we're going to say is, let's say what happens when we approach 0. What happens when that change approaches 0? Not what actually happens there, but when it gets closer and closer and closer. And that's where we get the slope of the tangent line. So the tangent line is the instantaneous rate of change. So going back to the example I said, driving the car 6 miles in 6 minutes, what does that mean that I'm going 60 miles per hour the entire time? Not necessarily. I could be going faster. I could be going slower. That is going to be our instantaneous rate of change. So let's get into it. This limit process is something that we used in chapter 1, and you should have seen this in pre-calculus. So the slope of the tangent line is going to be the limit as delta x approaches 0. Plugging in f of x plus delta x, plugging in f of x over delta x, we simplify to this expression 2x. What that means is, given this equation, y equals x squared plus 1, so given that equation, the slope is going to be dependent purely upon what x value we end up being at. The x value that we end up being at is going to be, in this case, listed in the problem, x value of -2. So if I plug -2 into the equation, and this is the equation for slope, if I plug -2 into that equation for slope, you'll see that that slope is -4. And I always like to do a visual check. So visual check, this is a parabola that opens like this. So the parabola opens like this. at x equals -2, it seems reasonable. The slope there is going to be -4. And then an extension of it, where is the slope perpendicular to 3x minus 4y equals 2? That equation graphed is approximately like this, because the y-intercept is negative, the x-intercept is positive. So we're expecting somewhere in this region, that's where we're going to have a perpendicular slope. So the first thing we have to do is determine the slope, which I said is 3/4. So the slope of this line is 3/4. The perpendicular slope is -4/3. And what we do is we set the slope of our tangent in terms of x equal to that -4/3. And in the end, we get x equals -2/3, which sort of matches up with the graph that I have there. So I feel like I'm on the right track. This whole process of finding the slope of the tangent line, and we're using the slope of the tangent line to create an equation. And I want to stress this is an equation based off of x. So this equation is our slope. We're used to seeing slopes as actual numbers, but now we're having slopes as equations. So the slope as equations, that's what we mean by this term derivative. The derivative is the equation, you can see it right here, of the difference quotient. The difference quotient is what we just used. So the derivative is that difference quotient applied to a function. We have like several different ways that we can describe it. This process is called differentiation. We could say the function is differentiable if the derivative exists, and we'll talk a little bit more about that. But the idea is all of these are related to the derivative. So quick check on your knowledge. Given f of x equals -5x plus 3, our goal is to find f prime of 2018. Well, f prime, and I know I just read that, f prime is the notation that we use for derivative. I think I skipped over it. I'm just going back to it. But f prime is the notation for derivative. So this says the slope at the x value of 2018 is -5. And the reason why I know it's -5 is because this is where I know this line has a constant slope of -5. So that's why our slope is going to be -5 there. As we go through the notes, what you'll find is a lot of these skills that we are doing right now, we did in chapter 1, which is why those are in there in chapter 1. So if our goal is to find f prime of -2, well, first I'm going to take the limit as delta x approaches 0, f of x plus delta x minus f of x over delta x. Okay, you'll hear me say this over and over again. Now to simplify, this is where if we plug in 0 for delta x, by plugging in 0 for delta x, we get that 0 over 0 mentality. By the way, that's very important to write it that way, but that 0 over 0 is what indicates we have to reduce, or we have to remove the discontinuity that's going to occur, just to use the terminology we talked about last time. So when we remove the discontinuity and we go through the algebra and jump through the algebra, we're going, and then at this point, we can plug in -2 to the equation, we get a slope of 1. Now what I've done here is I've said, okay, I know that f of -2 is 1, I can create the equation of the tangent line from it. So that was just an extension I did with this problem. Part B, same thing, where our goal is to find the slope of f at x equals 3. So really, I like to, right from the beginning, say, that means I'm going to find f prime of 3. To find f prime of 3, first thing I'm going to do is find f prime of x. And I found f prime of x by limit as x approaches 0, delta x approaches 0, f of x plus delta x minus f of x over delta x. If you remember, to simplify rational functions, we're going to multiply by the LCD of the denominator, which is going to include both of those, and then over itself. And go through the math until we get to this expression, which is the derivative. So then when we plug in 3 to our derivative, we get a slope of -3/25. And that's our overall solution. So this definition of derivative, the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, aka the difference quotient with limits attached to them. We do have an alternate definition of derivative. That alternate definition of derivative allows us to find this, and that's f prime of c. Now, a big difference is this tells us specifically a slope at a point. So where the definition of derivative gives us an equation for the derivative everywhere, The alternate definition allows us to find the slope at a point, and that's at a single x value. So once again, we're going to talk about the slope of the secant line where I have a set point. In this case, my set point is c comma f of c. Well, now I'm going to generalize and say I have some random point x comma f of x out there. And if I find the slope of that secant line, y2 minus y1 over x2 minus x1, we get this expression, which is the limit as x approaches c. Now, the visual on that is x gets smaller and smaller, gets closer to c, which means this point goes to here, goes to here, goes to here, and goes to here. So, but we have the limit as x approaches c of f of x minus f of c over x minus c. And again, the whole point of this is to find the slope at a single point. And the benefit is, what happens if I really don't want to go through all the different math just to find the equation for everywhere? What happens if I just want to know one point? This one's going to be completely valid, such as in this situation. So if I do the actual definition of derivative, I'm going to end up with like x plus delta x cubed. And then, I mean, really, it's a big algebraic, I'm going to call it funness. I almost said mess, but it's going to be algebraic funness. I don't mind doing that, but we don't really have to do that if we have this alternate definition. And our goal is just to find the slope at the point 2 comma 11. So if I'm finding f prime of 2, then I'll take the limit as x approaches that c value that of 2, f of x minus f of c over x minus c. So it's not a bad idea to get in the habit of writing that slope formula down until you know it and you know it well. And then we go through the math, and now one of the things I'd like to point out is right here. If I plug in 2 to the equation, I get 0 over 0. And by plugging in 2 to the equation, we get 0 over 0. That tells me that there is a removable discontinuity somewhere, which leads me to say, oh, we can use synthetic division to factor because I know I have my x minus 2 in the denominator. And it turns out it works. So then when I remove my discontinuity, I'm left with the limit as x approaches 2 of x squared plus 2x plus 6, which gives me 4. So a nice happy answer. Part B, same thing. The limit as x approaches c, f of x minus f of c over x minus c. And then we say, okay, what kind of equation results out of this? And this would be the radical expressions that we talked about before. And those radical expressions that we talked about before, we know that we have to multiply by the conjugate in order to simplify, which we do. We get down to here. And then please notice that I dropped the limit notation going from here to here because I'm plugging in the 7 to get an overall slope of 1/3. Now, if I look at C, C is going to be the first example of us, let's use the limit definition or the alternate definition derivative to prove why things don't exist or why the derivative does not exist. So let's take a quick look at the visual of this graph. This absolute value function has the vertex at x equals -3. And the question really is asking, what is the slope at that vertex? And for anybody who knows, it's like, okay, well, is the slope going to be +1 or is the slope going to be -1? What's going on there? The slope's not the same. Since the slope's not the same from the left and the right, we are not going to have a derivative that exists here. And as we go ahead and do the alternate definition of derivative, limit as x approaches c of f of x minus f of c over x minus c. If you remember, it turns into an expression that you use in chapter 1 quite a bit. And excuse me, we know that this limit doesn't exist because this turns into 1 and -1 based off of which part of the graph you're on. Need to pause. All right, I'm back, everybody. Just a little bit of a coughing fit. I apologize. So going back to what I was saying was that this is a piecewise function. This is 1 when x is greater than -3. That's -1 when x is less than -3, which tells us that the limit from the left doesn't equal the limit from the right. Now keep in mind this limit from the left and the limit from the right represents the derivative. And so this derivative at x equals -3, since the limit doesn't exist, means we're not differentiable at x equals -3. The cool thing is to note that the slope of 1 from the left, we can visualize right here. And the slope of -1 from the right, we can visualize right here. So everything matches up, which is very, very cool. Visually, we can see that there's a cusp there. So a cusp indicates that the slopes aren't the same from the left and the right. In pre-calculus, I tell my students means that it's smooth. So the fact that this is not a smooth function means the derivative doesn't exist. Second case, x to the 1/3. X to the 1/3, we can see on the graph that I have here that this x to the 1/3 graph has a vertical tangent, and a vertical tangent has an undefined slope. And sure enough, as we do the limit alternate definition of derivative, then we can see that we end up with 1/0, and 1/0 is an undefined slope. So our second case of where things are not differentiable is when you have an undefined slope, which is a vertical tangent on the graph. And then I have some work here that's asking students, what do we have continuity? And if you remember, to prove continuity, we have to use the limit from the left equals the limit from the right, and those two are the same. So the limit exists, the function exists, and the two are the same. And because the two are the same, we have a continuous function. So 5a is continuous, but if we do the limit definition, and by the way, I stole this 2x because it's the exact same equation that was on the previous problem. So we know our derivative is 2x. The slope from the left does not equal the slope from the right at x equals 1. So the slope from the left is 1, the slope from the right is 2. That means that these come together. It's a continuous function, but it comes together at a sharp turn or a cusp. For number 6, we don't have continuity, and since we don't have continuity, then we don't have differentiability. So no continuity, there's no differentiability. But continuity does not imply differentiability, and so I do want to summarize that. So continuity does not imply differentiability. Differentiability, however, will imply that we have a continuous function. And that's going to be something that's really important, especially when we get into describing and arguing why things are true and not true. So the 3 reasons why a function is not differentiable. Function is not continuous. We just saw an example of that on 6b. Slope from the left doesn't equal the slope from the right. We saw that on 6a, as well as the cusp problem on the absolute value graph, where the slope is undefined because we have a vertical tangent, which we saw on the x to the 1/3 graph. And then example 7, just kind of like a quick connection. Do we understand the notation g of 2 is going to be the value at 2, and g prime of 2 is going to represent the slope? And we have to do the slope numerically here, y2 minus y1 over x2 minus x1. In 2.2, excuse me, in 2.2, we're talking about our derivative rules. First rule in derivatives is what we call the constant rule. And the idea behind the constant rule is what happens if we have a horizontal line. Like a horizontal line of y equals 3, we know has a slope of 0. And so since the horizontal line has a slope of 0, we can say f prime of x is going to be 0 everywhere. Now, this is just a little bit of a limit proof to show why that's true. Keep in mind that this does not yield a 0 over 0. This is 0 over a very, very, very small number. And so 0 over anything then is going to be 1. The second rule is the power rule. The power rule says that if we take the exponent, we can bring the exponent out in front, and then we drop the exponent by 1, and thus that's how a power rule occurs, where our derivative is going to be n times x to the n minus 1. We ended up seeing that in the first section, and then I'm going to focus on the x squared. The x squared, its derivative, we bring that 2 out in front and drop the exponent by 1, get 2x to the first. And then we could show the constant rule here, the derivative of that constant 1 is 0. I threw an extra x squared on here. So here's our proof behind it. The proof really uses the binomial theorem. It's a great opportunity to bring in some of that random math that we don't always see. So x plus delta x to the nth power. If we use a binomial theorem, it'll be n choose 0, x to the nth, n choose 1, x to the n minus 1 delta x to the first, et cetera, et cetera, et cetera. What happens, like always, all the non-delta x terms cancel out, which I already have written there for you. And then when I factor out that delta x from the rest, so when I factor the delta x from the rest, what happens is this right here, this is the only term that does not have a delta x. So that when I plug the limit in there, That's the only term that does not have a delta x. So n times x to the n minus 1. And then the constant multiple rule, what the constant multiple rule says is, if we have a function times a constant value, we can take the derivative first and then multiply it by the constant value. So it's not something I really focus on specifically because students seem to intuitively get it. Example number 1A, if f of x equals -2, my thought process behind that is, hey, that's a constant function which has a slope of 0. Part B, if we rewrite it first, we rewrite this so that it's in its power rule form, x to the -7th. So x to the -7th. Like before, we bring the exponent out in front and then drop that exponent by 1, which is how I get -7 over x to the 8th. For C, one of the big things that we need to make sure we keep in mind is this function is not differentiable at x equals 0 because it makes, or it's not continuous at x equals 0. We have the 0 is 0, which is a discontinuity. So once we remove the 0 by reducing, then we have this expression, x to the 9/2, which is how we're going to find the slope everywhere else. So when x equals 0, the slope's undefined. And then when x is something else, we have 9/2 x to the 7/2. For 2, 2 is just going to be find the equation of the tangent line. So I threw this in here to have a little bit of extra math, do some work with radical expressions. Can you turn 1 over x to the, or the cube root of x squared, can you turn that into x to the -2/3? Just kind of a quick refresher on some radical skills. Our derivative, we still do this by the power rule, bring that exponent out in front, and then -2/3 minus 1 is going to be, so -2/3 minus 1 is how we get -5/3. Continuing on, in order to find the equation of the tangent line, the equation of the tangent line requires that we have a point. So I found the point, and it's not a very pretty point, unfortunately. Because it's not a pretty point, we're going to have to just do some reducing if we want to, and I don't really, so I'm going to say I'm going to leave it in that form. Example 3 begins our Leibniz notation. So the f prime notation is primarily Newton. The dy dx is the Leibniz notation. Now, when it comes to that Leibniz notation, I want to stress that I encourage and highly encourage and strongly encourage you to use dy dx because I'll tell you why in just a second. So dy dx represents a couple different things. You can look at it as change in y over change in x. That's not exactly what it is right there, but it's close enough, at least for what we know right now. It's officially the differential in y over differential in x, and we'll talk about that at the end of chapter 3. Change in y over change in x, aka slope. So the derivative of our function y with respect to x, which is another way that we could write it, is 8x to the 3rd if we use the power rule. On part B, 4/3 times 3. And hopefully you know that 4/3, tool again. We know that 4/3 times 3 gives us 4, and then we drop the exponent by 1. On C, if we rewrite it first, I highly encourage all of the rewriting. And then take that -3 times 5 to give you -15/2, and then drop the exponent by 1. So keep in mind, x to the -3 minus 1 is x to the -4th. D, in order for us to be able to work with D, first we have to simplify the expression in the denominator. So that once we do that, we have 5 over 8x cubed, which rewriting again is 5/8 x to the -3rd power. So I take the derivative, we have -3 times 5/8, and then x to the -4th in the denominator one more time. E, just one more time, doing some work with radical functions. Can you write radical functions in their rational exponent form? And I prefer the rational exponent form mainly because turning it back into a radical makes it look a lot more complicated than it needs to be. Having that, that rational exponent is very nice. Now, one of the reasons why I like the dy dx notation and not y prime, if you say y prime, you don't know what your independent variable is. So I refuse to use y prime until we do some work with differential equations. We're going to do that at some point soon. But y prime really has its use in differential equations because what is y prime? does y prime have an independent variable of t or an independent variable of x? Which is why the Leibniz notation of dy dx is better, because that tells us that our derivative with respect to x is going to be 0, because that implies t is going to be a constant. Dy dt, however, we can apply the power rule to it, where the derivative of y with respect to the variable x, or variable t, is going to be 8/5 t. Sum and difference rules, things I want to highlight with sum and difference rules. Derivatives are done term by term. And since derivatives are done term by term, we could say, all right, our derivative of -3 theta to the fourth, and by the way, theta is our independent variable, power rule of the second term, and then power rule for the third term is going to be plus 0. All of our derivatives, I really want you to write your derivatives in terms or in factored form. So fully factored form is going to be the result all the time. I'll explain why in just one moment. For part B, derivative, power rule, -4 times that, 4 times -1/2. This will be 2 times 3, and drop the exponent. And then this one has an exponent of 1, so if we drop the exponent by 1, that's y to the 0 power, which is just 1. This problem cannot factor, so I guess we could take a 2 out. I'd prefer really the whole point of factoring is to factor out the variables, not factor out the numbers. So if you didn't factor this any further, you're okay. For part C, first we rewrite it, and the rewriting that I did was 4t to the -2nd plus 3t squared. Once again, -2 times 4 will give me that -8. Drop the exponent by 1. 2 times 3 is 6, and then drop the exponent by 1, and you know that we don't have to write that 1 as an exponent. But once again, factor it out. To factor it out, we have to look for the GCF of the coefficients and the smallest exponent. And in doing so, that gives us an expression that, excuse me, that gives us the expression 4 minus 3t to the fourth, which I can then combine into one overall equation. If you notice, I multiplied the negative back inside just because I prefer to have my t to the fourth in front. For D, if we apply the power rule, 5 halves x to the 3 halves, 9 halves because of 3 halves times -3, and then 1/2 times 4 gives me the 2. Drop the exponent by 1. If we factor out the x to the -1/2, and we also factor out this fraction of 1/2, what ends up happening is we have an expression which looks like so. And do the math, we can put it together into this one nice expression, which allows me to go back through and say, okay, why do I want everything in this factored form? Because in this factored form, if I take a look at 5x squared minus 9x plus 4, let's open up Desmos really quickly and wait for it to load. Probably should have had this loaded up already. So 5x squared, 5x squared minus 9x plus 4, and go back to notability, over 2x to the 1/2. So divided by 2x to the 0.5. What this allows us to see, if I zoom in, that I have, a horizontal tangent at, this ends up being 2 of these spots. It doesn't look like it, it's kind of hard to see it, but we end up with horizontal tangents as those x values. The horizontal tangents are going to be a key component of what I want to do, or what we want to do in the calculus, because our derivative, what's the point of doing the derivative? What's the point of finding all these slopes? We want to know where the rates of change are 0 or undefined, because we can then say, where is our instantaneous rate positive? Where is our instantaneous rate negative? So this changes at zeros and undefines, and so it's going to be essential for us to figure these out. All right, derivative of sine is cosine, and the derivative of cosine is negative sine. I like to show this one graphically. If I take this as my sine graph, let's do this part in, let's choose pink. The slope here is 1, the slope here is 0, Slope here is -1, slope here is 0, and the slope here is 1. We graph the slopes, we can see that it is the positive cosine graph. And similarly, let's choose another color, let's go brown. So the slope here is 0, the slope here is -1, slope is 0, slope is +1, and the slope is 0. We can see that the slope of the cosine graph is the negative sine graph. So, and the derivative of the natural exponential function. So basically the derivative of e to the x is itself, which is very, very cool, but that's why it's called the natural number, because it's its own rate of change. And so I showed a small proof here. It's easier to show this one numerically. I stated it, but I didn't actually show it. For problem number 5, this is just some problems, practice problems. The derivative of sine is cosine, the coefficient doesn't change. Derivative of x is 1. Derivative of negative cosine is positive sine. Derivative of sine is cosine. I rewrote this to begin with, 4 over 7a e to the x, and that way, because if I take the derivative with respect to x, which is what I was asked to do, that a ends up just being a coefficient, or at least it's a constant variable, so it's a part of the coefficient. So the derivative is really itself. And similarly, derivative of 3 e to the x is itself. Power rule, 2x to the 0 power, and derivative of -4 cosine is positive 4 sine. And these problems, which I know I didn't talk about in class, but these problems represent real life context of what's going on. So just in terms of, do you understand notation, what it means? So if we have cost as a function of W, that means 12 represents the weight, and that means 5 represents the cost. So the cost of purchasing, that should be 12 tons of a chemical. I'm not sure how that error got through. So the cost of purchasing 12 tons of the, pause 1 second, I'm having a small issue. All right, so a small issue I had was my pen died. So it's the cost of purchasing 12 tons of a chemical is $5,000. We expect F prime to be positive because as weight gets higher, the cost will be higher, so we should have a positive derivative. So you guys think about this in terms of correlations and relationships. If they're positively correlated, they're going to have a positive slope. If they're negatively correlated, they have a negative slope. Our statement, the cost, and once again, wrong tool. The cost of producing 12 tons, since it's the derivative, is that cost at that moment when purchasing the 12 tons is 400 tons per hour. I got $400 per ton, excuse me. I got that 400 because 0.4 thousand, which gives me the 400. If we look at some numerical data, where do we have the estimate the marginal cost? So we're going to do this through average rate of change. Since we have physical data, then we're going to measure the physical data through the average rate of change. So that physical data of average rate of change approximates the instantaneous rate of change. And then we say, where is that the smallest? So we take a look and see where we have the smallest change. So from here to here, we have the smallest change. So maybe you can argue around 2,200, 2,300 tons. So there's a very bit of openness to that equation. Just a quick introduction to position, velocity, and acceleration functions. Specifically, the derivative, the position function is 1/2 the gravitational force t squared plus initial velocity times t plus initial position. S prime is our instantaneous velocity, and S double prime will be our instantaneous acceleration. I'm not really asking for any of that right now. So our position function, since I know that this is in feet and then this is feet per second, then I know that I'll be using -16 feet per, or -16, because it'll be -32 divided by 2. Initial velocity, it's being thrown down from the top of the building at 22 feet per second, which means it's a negative velocity. Then plus 220, because that's my initial position at 220 feet. Our derivative is going to be our velocity function. So this will be our velocity, negative 32t minus 22. Then to find the ball's velocity after 3 seconds, it's really saying what is s prime or v of 3. Last but not least, if I want to find the velocity after falling 108 feet, keep in mind if I fall 108 feet, then we are at 112 feet now, which then when I bring to the other side, that's where the 108 is going to show up. And then we do some math, and I showed some factoring. Most students tend to solve this by quadratic formula, which is fine. So our answer ends up being at time 2. And at time 2, we have negative 86 feet per second. So hope you enjoyed learning a little bit about the calculus, and I look forward to seeing you guys in class next week. Have a good weekend.